Today, we're diving into, well, one of the most intriguing concepts in physics, quantum entanglement.
Absolutely fascinating stuff.
Yeah, and a listener recently sent us a truly thought-provoking question. It highlights what feels like a paradox, really, at its very heart.
Okay.
How can entanglement be spooky action at a distance? Where particles are perfectly linked no matter how far apart.
Right, the instant correlation.
Exactly. Yet, require those same particles to be practically touching to be created in the first place. It certainly makes you wonder, doesn't it?
It absolutely. We'll explore how the non-local character of an established entangled link, that's a property of the quantum state itself. While the need for proximity in its creation, that's a feature of the dynamic physical processes needed to actually generate that state.
Got it. So, get ready for some truly mind-bending moments because we're about to explore the quantum world.
Let's do it.
Okay, so our journey into entanglement, it really begins with superposition.
Mm-hmm.
Imagine a quantum bit, or qubit. It isn't just a 0 or a 1, but kind of a blend of both. A quantum cloud of possibilities until you look.
Like being both heads and tails at once for a coin flip before it lands?
Exactly. Think of it as being able to be both on and off at the same time. And this isn't just some mathematical trick. It's the fundamental reason quantum computers can explore millions of solutions simultaneously.
A capability classical computers simply can't match.
Right.
Now, when you extend this principle to two or more particles, you get inseparability.
Inseparability.
Yeah. An entangled state cannot be described by just looking at each particle individually. Their quantum states are linked, woven together no matter the distance.
So they're not independent anymore.
Not at all. A classic example is what's known as a Bell state. If you have two entangled qubits, say A and B, and you measure qubit A as a 0,
Okay.
you instantly know qubit B will also be a 0 with absolute certainty, regardless of how far apart they are.
Wow, okay. The connection is instant and absolute.
That's the core idea.
So we've established how individual particles can be, well, bizarrely linked across vast distances through superposition and this inseparability.
Mm-hmm.
But this mind-bending phenomenon naturally leads us to the historic moment where this spooky action first truly challenged our understanding of reality. The EPR paradox.
Ah, yes. Einstein, Podolsky, and Rosen, 1935.
Right. They argued that quantum mechanics must be incomplete if it allowed such instantaneous connections. They based their argument on something called local realism.
Local realism. It rests on two very intuitive beliefs. First, locality. Basically, influence or information can't travel faster than light. Nothing does.
Standard physics, yeah.
And second, realism, which states that objects have definite properties even when no one is observing them. A tree falling in the forest does make a sound.
Okay. Seems reasonable.
So the EPR argument went like this. If measuring qubit A instantly tells you qubit B's state, and if locality holds, then B must have already had that property predetermined.
It had to know beforehand.
Exactly. They thought there must be hidden variables, some underlying yet-to-be-discovered information that would complete the theory.
Like cheat sheets the particles carry.
Kind of. It's like trying to explain Dr. Bertelmann's mismatched socks. If one's pink, you instantly know the other isn't.
Right.
Not because of spooky action, but because he chose mismatched socks that morning. They were already set.
So they thought quantum mechanics was just missing those hidden instructions.
Precisely. For decades, this was largely a philosophical debate, a fascinating thought experiment.
Just talk, no proof either way.
Exactly. But then, in 1964, John Stuart Bell devised a way to actually test it.
Bell's theorem.
Bell's theorem. It proved that no local realist theory, no theory with those hidden variables can reproduce all of quantum mechanics' statistical predictions.
So it put math behind the philosophy.
It did. He derived Bell inequalities, which are mathematical rules or limits that any everyday, non-spooky correlation must obey.
Like the maximum amount of correlation you'd expect classically.
Exactly. But quantum mechanics predicts correlations stronger than these classical limits, correlations that effectively break those rules.
Wow. Okay.
And this wasn't just theory. It was put to the test in landmark experiments. You mentioned Clauser, Elaine Aspect, Anton Zeilinger.
The Nobel Prize winners, yeah.
That's them. Aspect's 1982 experiment was pivotal. He famously closed the locality loophole by changing measurement settings mid-flight after the particles had left their source.
So there was no time for a light-speed signal to coordinate things.
Precisely. Subsequent experiments closed other loopholes, like making sure the detectors were efficient enough. And the results solidified this shocking conclusion. The world is not locally real.
It's not locally real.
The correlations are stronger than classical physics allows, and their strength, that unbreakable link, it doesn't diminish with distance.
Wow, so it's not just a theory. It's been experimentally proven that the world isn't locally real. That's a pretty fundamental shift in how we understand reality.
It really is. It's like finding out gravity sometimes pushes instead of pulls, as you said. It changes everything.
Given this astounding confirmation of spooky action at a distance, it naturally leads to a crucial question.
Yeah.
Can we actually use this spooky action to send messages faster than light? Is this the ultimate communication breakthrough?
The million-dollar question, and the answer is unequivocally no.
No, but it's instantaneous correlation.
It is, but here's the catch, guaranteed by the no communication theorem, and here's why that's actually fascinating in itself.
Okay.
While Alice's measurement on her entangled qubit instantaneously correlates with Bob's, Alice's outcome is fundamentally random. She gets a 0 or a 1, but she can't choose which one she gets.
So she can't force her qubit into a specific state to send a dit or a da in Morse code, for example.
Exactly. She can't control the message content. Bob, observing his qubit alone, just sees random data. 0, 1, 1, 0, meaningless noise.
So the correlation is hidden in the randomness.
Precisely. The profound correlation only becomes apparent after they communicate classically, phone call, email, shouting across the lab, something limited by light speed, and compare their results.
Okay, so they both have random lists, but when they compare them, they see the perfect correlation.
That's it. So while the correlation itself is non-local, instantaneous, the transmission of usable, meaningful information remains strictly local and causal. Relativity is safe.
Whoa. Physics holds together. It's a beautiful way it keeps its rules consistent.
Isn't it just?
Okay, so if this established entanglement persists across vast distances, as we've seen, that brings us right back to the central paradox you raised in your query.
Right.
If it's so boundless once created, why do quantum engineers always talk about the painstaking need for particles to be in close proximity to actually make entanglement? What's going on there?
That's the heart of the matter. The generation of entanglement is an active, dynamic process. It's not a passive property that just appears out of nowhere.
You have to do something.
You have to do something, and that something universally requires direct physical interactions between the particles.
They have to talk to each other directly.
In essence, yes. They need to feel each other's presence through some local force. In quantum mechanics, this means the system's evolution, its change over time, must be governed by an energy equation, a Hamiltonian, that includes a local interaction term, a piece that couples the particles.
And all known physical interactions are local.
All known fundamental physical interactions, yes. Electromagnetism, the nuclear forces, they act locally. You can't just wish entanglement into existence across a room. You have to put in the work locally.
This proximity requirement is universal then. Across all the different ways people are trying to build quantum computers.
Absolutely universal. Let's look at some examples.
Okay.
Take semiconductor spin qubits. These are like tiny artificial atoms in silicon. Here, entanglement uses the exchange interaction.
Exchange interaction.
It's a uniquely quantum effect that only happens when the electron wave functions, their quantum clouds, literally overlap.
So they have to be really close.
Incredibly close. Its strength decays exponentially with distance. We're talking nanometer scale precision, typically less than 100 nanometers, to perform an entangling 2-qubit gate.
Nanometers. That's practically touching.
It basically is on an atomic scale.
Okay, what about another approach, like neutral atoms?
For example, neutral atom arrays. Here, you trap individual atoms with lasers. To entangle them, you excite them to giant, puffed-up states called Rydberg states.
Giant atoms.
Relatively speaking, yes. Their electron orbits are huge. The interaction between these large atoms is a van der Waals force. It's incredibly strong up close, but it falls off extremely rapidly with distance. It scales as 1 over r to the 6th power.
1 over r6. That's a very sharp drop-off.
Extremely sharp. And this rapid decay creates something called the Rydberg blockade effect.
Blockade.
Yeah. Within a certain distance, maybe a few micrometers, exciting one atom to a Rydberg state physically prevents its neighbor from being excited by the same laser frequency. It's like one atom blocks the other.
So that gives you the conditional logic you need for entanglement. If atom A is excited, atom B can't be.
Exactly. But the key point is the absolute necessity of placing atoms within this blockade radius. They have to be within those few micrometers.
So again, proximity is crucial for the interaction.
Fundamentally crucial. What these varied examples all reveal is a profound truth. While entanglement's reach is boundless once formed, its birth is brutally constrained by the physics of direct local interaction.
And that's a primary engineering hurdle for every quantum technology, I imagine.
A massive one.
Okay, one more example. Trapped ion systems. They use the Coulomb force, which is long range, right? Like charges repel, opposites attract.
That's true, the underlying force is long range. But here's the clever trick. Instead of the ions interacting directly with each other's charge state, their motions are coupled together.
They're physical jiggling in the trap.
Exactly. They're coupled into shared collective vibrational modes. Think of them like tiny quantized sound waves traveling along the chain of ions. We call them phonons.
Phonons, like a quantum bus.
That's a great analogy, a quantum bus. These phonons act as the intermediary, allowing the ions to communicate indirectly.
So how does that link to entanglement?
Lasers are used very precisely to couple an ion's internal state, its spin, the 0 or 1, to these shared motional modes, these phonons.
So you map the qubit state onto the vibration and back again.
Essentially, yes. You use the shared motion to pass quantum information between ions. But while the underlying Coulomb force is long range, the actual high-fidelity entangling gates still practically depend on the ions' proximity and their precise positions within the trap.
Why? If the force is long range.
Because the shared motion, the phonon bus itself, is born from their collective proximal arrangement. The strength and control of that coupling relies on them being close and well-ordered. So, even with a seemingly long-range force, the mechanism of entanglement creation is still effectively local.
Fascinating. It always comes back to needing them close by to kick things off.
It really does.
But that raises another question. What about entanglement swapping? I've heard about this. It sounds like two particles, let's say A and D, can become entangled even if they've never directly interacted or even been in the same location.
Oh, good point.
Isn't that a direct contradiction to everything we just said about proximity being essential for creation?
At first glance, it absolutely seems that way. And entanglement swapping is incredibly important. It's the foundational principle for things like quantum repeaters and the future quantum internet.
Okay, so how does it work without contradicting the proximity rule?
Here's the setup. Particles A and D are distant, maybe miles apart. But A is initially entangled with a partner, B, and D is entangled with a partner, C.
So you have two separate entangled pairs, A, B, and C, D.
Right. Now, you send the inner partners, B and C, to some central station in between A and D.
Okay, B and C meet up.
At that central station, you perform a special kind of joint measurement on B and C. It's called a Bell state measurement, or BSM.
Measuring B and C together.
Exactly.
Yep.
And the outcome of this measurement on B and C has a remarkable effect. It projects the distant particles, A and D, into an entangled state, even though they never met.
Wow. So A and D become linked just because B and C were measured together.
Correct. But, and here's the crucial point, the Bell state measurement itself is a local process. To measure B and C jointly, they have to be brought close together at that central station.
Ah. So the locality requirement hasn't vanished, it's just shifted to the measurement step.
Precisely. The BSM requires proximity. It consumes the pre-existing entanglement in A, B, and CD through a local interaction and measurement, and uses that to effectively stitch together new long-distance entanglement between A and D.
That makes sense. It's like building a long bridge by connecting smaller sections, and each connection happens locally.
That's a perfect analogy. This protocol beautifully illustrates that long-distance entanglement is an incredibly useful resource, but it can only be established through a carefully orchestrated sequence of local, proximity-dependent operations.
So, no free lunch.
Yeah.
You still need local actions to build the non-local connection.
No free lunch. And this raises another important question. If it's so hard to create it, what about keeping it? But before that, let's think about scale.
Right. Our discussion has mostly been about just two particles. But what happens when we're talking about entanglement between, say, two large systems of particles? Does the percentage of particles which are entangled change, or does it become much more complex than just two particles being linked?
Oh, the transition to many particles dramatically increases the complexity. It's not just a simple separable or entangled anymore. There's a whole hierarchy.
Hierarchy.
Yeah, we talk about things like K-separability. That means entanglement exists, but only within groups of at most k particles. Maybe pairs are entangled or triplets, but not the whole system together.
Okay.
And then there are what we call genuinely multipartite entangled states, or GME states.
Yeah.
That's where all n particles in the system are irreducibly linked. You can't describe the entanglement by breaking it down into smaller groups.
So it's like, is it just pairs holding hands?
Hmm.
Or is everyone in a giant group hug that you can't break apart?
That's a pretty good way to put it. This complexity is a significant challenge for scaling quantum technologies, both understanding it and creating it.
And a classic example of this complexity, I think, is seen in 3-qubit GME states, right?
Exactly. Consider the GHZ state, named after Greenberger, Horn, and Zeilinger.
Okay.
It's a state where all 3 qubits are perfectly correlated. Think of it like 1,000 euro and 111 euro existing simultaneously mixed together. It's an all-or-nothing kind of entanglement.
All or nothing.
Yeah, if one qubit is lost or disturbed or measured separately, the entanglement of the entire 3-qubit system is destroyed. Gone.
Wow. Very fragile then.
Extremely fragile. In contrast, there's another famous 3-qubit state called the W state.
The W state.
Yes. It's a superposition of states where just one qubit is a 1 and the other 2 are zeros, like 100 euro, 0, 0, 0, 0, and 0, 0, 0, 1. You're all mixed. This one is more robust.
How so?
If you lose one qubit from a W state, the remaining 2 are still entangled with each other.
Ah, okay, so losing one part doesn't destroy the whole connection.
Exactly. These are fundamentally distinct types of multipartite entanglement, each with different properties, different robustness, and potentially different uses.
It's getting complicated fast. How do we even begin to quantify the strength, or maybe that percentage, of entanglement in these complex systems? It feels less straightforward than just linked or not linked.
You're right. It's much more nuanced. We use mathematical tools called entanglement measures. One very important one is entanglement entropy.
Entropy. Like disorder.
Related, but here it quantifies uncertainty due to entanglement. Imagine you divide your many-particle system into 2 parts, A and B. The entanglement entropy of part A measures how much uncertainty you have about A because it's entangled with B.
So the more entangled they are, the less you know about A by itself because its state is tied up with B's.
Precisely. If they weren't entangled at all, the entropy would be 0. If they're maximally entangled, the entropy is maximal.
Okay, that gives a quantity. What about the structure, the group hug versus pairs holding hands idea?
For that, we look at things like entanglement depth. This directly addresses your question of percentage or structure by giving a formal basis to how many particles are truly irreducibly entangled together in that GME sense.
So it tells you if it's 2-particle entanglement, 3-particle, or n-particle entanglement.
Basically, yes. It helps us understand the structure of the quantum correlations within the complex web.
So how does this entanglement actually grow within a large system? Does it just spontaneously appear everywhere at once?
No, it doesn't appear globally all at once. Remember our earlier point. The underlying forces and interactions in physical systems are local.
Right. Things have to touch or be very close.
So entanglement propagates. It spreads through the system over time. It's often described as having a characteristic light cone effect, similar to how influences spread in relativity, but related to the speed of interactions in the material.
Do you give an example?
Sure. Imagine you have a line of particles. An interaction between particle 1 and particle 2 entangles them. Then maybe particle 2 interacts with particle 3. This second interaction entangles particle 3 with the already entangled pair, 1, 2.
So the entanglement spreads link by link.
Exactly. And then 3 interacts with 4 and so on. This dynamic, propagating nature clearly shows that entanglement is built up via a sequence of local physical processes. It doesn't just pop into existence everywhere.
This locality of interaction, this spreading, does it lead to any general principles about entanglement in large systems?
It leads to a very profound organizing principle, actually, called the area law for entanglement entropy.
The area law. Okay, what's that?
If we connect this to the bigger picture, it turns out that for most typical many-body systems governed by local interactions, their lowest energy states, their ground states, aren't maximally entangled throughout the whole volume.
They're not all tangled up everywhere.
Generally, no.
Yeah.
Instead, if you consider a subregion within the larger system, the entanglement entropy of that subregion usually scales with the size of its boundary, its surface area, not with its volume, meaning the total number of particles inside.
Wait, so the entanglement depends on the edge of the region, not how many particles are inside it.
For ground states of locally interacting systems, yes, that's the typical behavior. And it's a direct consequence of the interaction locality we've been discussing. Entanglement is fundamentally generated at the boundary where interactions happen.
That's counterintuitive. You'd think more particles means more entanglement.
You might think so, but volume grows much faster than surface area. Think of a growing cube. Its volume grows as length cubed, but its surface area only grows as length squared.
Right.
So if entanglement scales with the area, it means that as the system gets larger, the fraction of particles involved in entanglement across that boundary actually gets smaller and smaller compared to the total number of particles.
So if you bring two large systems close together to interact,
The entanglement created between them will be primarily proportional to the area of their interface, where they touch. The percentage of particles that become entangled across the boundary will be small, and that percentage will shrink as the systems get bigger.
like your analogy of two giant amoebas touching the interaction, the entanglement is just at the surface.
Exactly. It confirms your initial intuition in a way. For large systems, the amount of entanglement generated is critically dependent on the proximity at the interface, and it's often predominantly a boundary effect.
That's a really key insight. Okay, now, you added a crucial but to your initial query earlier, mentioning decoherence.
Ah, yes, the enemy.
It sounds like this is the big spoiler for entanglement. What exactly is happening when entanglement decays or decoheres?
Well, in real world, no quantum system is ever perfectly isolated. It's just impossible. Every entangled pair, every qubit is unavoidably coupled, interacting with a vast, complex external environment.
The rest of the universe, basically?
Pretty much. Think thermal photons bouncing around, vibrations in the material, stray electromagnetic fields from, your phone or lab equipment. This unwanted interaction is the source of quantum noise.
And that noise causes decoherence.
It's the ultimate cause of decoherence, the loss of those fragile quantum properties like superposition and, crucially for our discussion, entanglement.
So how does this happen? Does the entanglement just vanish into thin air, like smoke?
Not exactly vanish, it's more subtle. The fundamental mechanism is that the quantum system you care about, say, your entangled pair A and B, becomes entangled with its environment.
Gets entangled with the noise.
In a manner speaking, yes. Imagine your pair A and B. A stray environmental particle, let's call it E, like a photon or a phonon, bumps into qubit A. This is a local interaction just between E and A.
Okay.
But that local interaction creates a larger tripartite entangled state involving A, B, and E.
So the entanglement spreads outwards to include the environment particle.
Exactly. Now, from the perspective of an observer like us who can only access and measure A and B, the information about the original A-B entanglement has effectively leaked into the environment, into particle E, which flies away. It's lost to us.
So the correlation is still there, but it's hidden in this bigger ABE system that we can't fully access.
That's the essence of it. Mathematically, what happens is the terms in the system's description, the density matrix, that represent quantum superposition and entanglement, we call them coherences, they decay towards zero. The quantum blurriness gets washed out.
And this is caused by local interactions.
Crucially, yes. The non-local quantum correlation between A and B is destroyed by a local physical interaction between one part of the system, A, and the environment E.
That's wild. So the environment essentially steals the entanglement. Even though it's just a local interaction with one particle, it doesn't just fade away, it actively gets absorbed or entangled with the surroundings.
That's a good way to think about it. The quantum information disperses into the environment's many degrees of freedom.
This sounds like it gets even harder than when you have larger quantum systems with more particles.
It absolutely does. The rate of decoherence generally increases dramatically with system size. Why? Well, a larger system simply presents a bigger target for environmental particles to interact with, more places for noise to creep in.
Makes sense.
And those many-body entangled states we talked about, particularly the GME states like the GHZ state.
The all or nothing one.
Exactly. They are exquisitely fragile. A single local decoherence event, just one stray particle hitting one of the qubits, can potentially collapse the entanglement of the entire global state.
Ouch. One hit takes down the whole thing.
It can for those types of states. Furthermore, think about building a quantum computer. You need to pack qubits closely together to make them interact for gates, right?
Yeah, because creation requires proximity.
But packing them closely makes them more susceptible to unwanted local interactions between each other. This is called crosstalk.
Crosstalk.
Yeah, like when the control signal intended for qubit 5 accidentally nudges qubit 6 as well, introducing errors. It's another form of local unwanted interaction.
So the very proximity needed to create entanglement also makes it more vulnerable to certain kinds of noise and errors.
Precisely. It underscores the local nature of decoherence mechanisms. The destruction of a global property entanglement is often caused by an accumulation of many small, local, unwanted interactions.
Which raises a huge challenge for the engineers, I guess.
A critical one. How do we make the desired local interactions for computation and entanglement strong and fast, while making the undesired local interactions with the environment or between qubits weak and slow?
That's the constant battle.
That is the constant battle in building quantum hardware.
Okay, let's step back and bring all these threads together. Your initial query about the paradox of entanglement strength, its non-local persistence versus its local genesis. Based on everything we've discussed, how can we now directly resolve that?
The key, I think, lies in understanding that the word strength is being used to describe two very different physical concepts in that query.
Okay. What's the first meaning?
The strength of entanglement for an existing pair refers to the persistence of its non-local correlation. That property confirmed by Bell's theorem, the fact that the correlation doesn't care about distance once established.
That's like a static property of the state itself.
Exactly. It's kinematic, a description of the state. It doesn't diminish with distance.
And the second meaning of strength?
The strength of entanglement between two systems of particles, or thinking about the percentage of particles which are entangled when you bring two systems together, that refers to the degree of collective entanglement you can generate.
And that's about the creation process.
Exactly. That's a dynamic process governed by those local interactions, the local Hamiltonian. And as we discussed, this generation fundamentally requires physical proximity.
And the area law tells us.
The area law tells us that for large systems, this generated entanglement is mostly a boundary effect. So the percentage of entangled particles is actually quite low compared to the total number, especially for bulk systems.
So the two strengths aren't in conflict because they refer to different things. One static property, correlation persistence, and one dynamic process, generation extent.
Precisely. Creating and destroying entanglement are dynamic processes requiring local proximity-dependent interactions. But maintaining an existing entanglement linkage involves a static property of the state whose non-local correlations are independent of distance.
That clarifies it perfectly. And this isn't just an abstract idea, is it? It profoundly shapes the architecture of all quantum technologies.
Absolutely. Think about quantum computing, those essential entangling two-qubit gates like the CNOT gate.
The workhorses of quantum algorithms.
They absolutely depend on bringing specific qubits close together, making them interact locally in a controlled way, and doing it quickly before decoherence kicks in.
Which leads to huge scaling challenges.
Immense challenges. Things like connectivity. How do you make any qubit talk to any other qubit if they all need to be neighbors? Crosstalk, which we mentioned. And just the practical wiring bottleneck. How do you get control signals in and out to millions of densely packed qubits?
It's almost impossible.
Very hard. A leading strategy to overcome this is modularity.
Modularity, yeah.
Yeah, build smaller, highly controlled quantum processing units, maybe a few dozen or 100 qubits each, where you can manage the local interactions well, and then find ways to link these modules together, maybe optically or through other interfaces.
So local control within modules, and then maybe entanglement swapping or something similar to link the modules.
That's a major direction, yes. It directly reflects this local generation, non-local resource reality.
And what about the quantum internet? You mentioned that earlier.
For the future quantum internet, this duality is its very foundation. The entire goal is to distribute that non-local persistence of entanglement over vast distances.
For things like fundamentally secure communication or linking quantum sensors.
Exactly. But again, you can't just generate entanglement directly between, say, New York and Los Angeles. The distances are too large, the loss is too great.
So how do you do it?
The solution is quantum repeaters.
Entanglement swapping again.
Entanglement swapping is the core mechanism inside them. These repeater networks will create entanglement over shorter, manageable distances locally, maybe tens of kilometers. Then they'll use entanglement swapping that local measurement protocol to stitch these short links together, progressively extending the entanglement over the entire network distance.
Link by link, using local measurements to forge the long-distance connection.
Exactly. The quantum repeater is a device conceived precisely to solve this problem, needing to use local means to create and distribute a fundamentally non-local resource. It's a perfect embodiment of the duality we've been discussing.
Wow. What a deep dive. It really feels like this duality, quantum mechanics being local in its dynamics, how things change and interact, but non-local in its state descriptions, the correlations themselves. That's arguably the most profound, powerful, and maybe weirdest feature of the quantum world.
I'd agree. It is the source of both the immense promise of quantum technologies and, frankly, the immense difficulty in realizing them.
How so?
Well, the non-local correlations enable the potentially exponential computational power and secure communication we dream of. That's the promise.
Right.
But the strict requirement for local proximity-based interactions for creation, control, and the susceptibility to local noise imposes these formidable engineering challenges we've touched upon. That's the difficulty.
So the journey to harnessing the power of the non-local quantum world.
Is and will continue to be fundamentally a journey of mastering the physics and the engineering of the local.
A journey of mastering the local to unlock the non-local. That's a great way to put it.
I think it captures the essence.
Well, thank you for joining us on this deep dive. We hope you, listening in, feel a little more well-informed and maybe even more curious about the strangeness and the potential of the quantum universe.
Thanks for having me. It was fun.